So we're now, so we have this model with a named and improved population. We have a model that exhibits death from heart disease and death uh, from a healthy heart, as well as death for a person with heart disease from other causes. This death is accomplished by removing people from the population. And when we run the model, we can see that there's some sort of competing processes involved where we have a growing number of people who have heart disease because they're developing it, but a higher rate of death of those people with heart disease. What we're going to now put into place is a mechanism for keeping track of information in this model. Specifically, we're going to have a bookkeeping mechanism that's going to keep track of the number of people with heart disease and without. So to do this, we're going to go to main, and we're going to go to the population. And then we are going to go to an area of the population we haven't used yet, haven't previously tapped. The statistics area of the population. Okay. And we're going to add in a statistic that's going to report the number of people with heart disease and without heart disease. So I did plus here. And this is going to be you could say count heart disease. So we've just gone to the population. We've pressed plus under the statistics area. We press plus. We're going to have a count statistic that's going to operate over the population, and it's going to count the number of people with heart disease. Okay. And in order to count them, we need some criteria to count. This is going to scan through the population, looking for people who match a certain criterion. And you'll learn about the criterion, something if you, once again, look at this little light bulb that's here under condition. So this is in for the population, the properties of the population in the statistics area. We've added this count heart disease. It's a count statistics, not an average, not a min, not a max, not a sum. And here it tells us use agent to refer to the agent in the population. So I'm going to say agent. And I'm going to ask if the agent is in a certain state. And that state is going to be heart disease. Okay. So I'm referring to this state, HART. Okay. But there's a little bit of a complication here we're going to deal with in just a sec for this, as we'll see. So that's what I'd like to be able to say. Like, are they in a heart disease state? The problem is it says, I don't know what heart disease is. I don't know the name heart disease. And this reflects the fact that we have to tell it what sort of heart disease. Are we dealing with canine heart disease? Or indeed bovine heart disease? Or indeed cervid heart disease? Or some broader type of primate heart disease? Or person heart disease? Well, here we're dealing with person heart disease. Okay. Notice the problems window came up again when I did that, because it's saying like, I don't understand what you mean. I don't know what heart disease is. See, if I clicked on this, it would have brought me there. And I said, like, I don't know what that means. Okay, here we go. So clicking on this, and now it's a happy camper. Now it's perfectly happy. So what did I do? I went to this statistic in population, and I had to tell it person's heart disease involving persons, not feline, not canine, not cervid, not ungulate, not bovines, more specifically, not broader primate. Yeah. Okay. So this is going to count the number of people with heart disease. I'm going to add one more. Count healthy heart, or count. I'm tempted to say no heart disease, but maybe I'll just say healthy heart to use the same term. And we basically mutatis mutandis. It's basically the same pattern. Agent dot in state, person dot healthy, and you can do autocomplete because autocomplete is your new friend. Well, yeah, it's part of any logic's toolbox. Yeah, it's part of its so-called API. It's part of its affordances that it offers to people who build models in state. Yeah. If you're wondering where those come from, I would note that you can go here and you can go to any logic help. And you can look at the library reference guides here. And find information on, for example, the API that you can use. And this would include information on particular things, like you should be able to look up in state, for example. And you could see that it's returns true if the corresponding state chart, blah, blah, blah. And it would let you find out more information about that. Okay, so now we have two mechanisms that can enumerate people in the population who are in different underlying characteristics. These are domain quantities of interest. Count heart disease, so count of people with heart disease, count of people with healthy heart. Let's build, make sure your model builds happily, and let's run. Okay. And you initially you won't see anything different, but if you go into the population, you'll find that it's tabulating the count of people with a healthy heart, the count of people with heart disease here. And it's reporting, of the population, the total, how many are in each state. Now, that's kind of nice, but we'd like to have something that's a little bit more visual, perhaps, than that takes advantage of the human visual cortex to recognize patterns. This is not a small matter. So we're going to go to main, and we're going to add in our first plot, a time plot. We're going to go to the palette and go to analysis in palette. and add in a time plot. And this will be called, so what did I do? I went to main. I want to add a plot to main to show the overall situation. So that plot needs to live in main. I went to the agent palette, excuse me, the analysis palette, and I dragged in a time plot. And I'm going to name that time plot in the properties window health time plot, health state time plot. And I use what's called camel case here. We could use underbars to separate things. Here we use capital letters to separate words. But there's a convention called snake case, which uses a different convention. But here we can call it health state time plot. Okay. And here we're going to be referring to those things in population that we just added. So the data of this is going to consist of two things. The first is going to be called, just a title, heart disease. It's not anything computational, so we can put spaces in it. And its value will be the statistic on the, or maybe I'll say count with heart disease. Or I could have said population count without heart disease. And this is going to refer to the statistic we just created. Where did that statistic live? Does anyone remember, where did we put that statistic in the model? Where does it live? It lives in population. That's where statistics live, in populations. It's a statistic over the population. So this time plot is going to refer to population dot count heart disease. Do we need a semicolon? The answer is, if my first PhD student would have said negatory, no, we don't need a semicolon because we're not telling it, do this, like make this change, make this happen, or make it alter this. We're not doing a command. We have a simple formula. It's calculating something. The count of people with heart disease. It's like a formula in Excel or Google Sheets. We don't need a semicolon. A semicolon is used when you're like changing something. Add this person to that. Update this variable. That's when we need a semicolon. Kind of like when it's an exclamation point. Imperative. So vocative in Latin or Sanskrit. Okay. So this is, we're going to add another one. I just did plus. This is going to be count with no heart disease. Yeah, that's right. This is going to be population dot count healthy heart. Where did this count healthy heart come from? Where did this count heart disease come from? Who created those? Who, pray tell, created those? We did. Not 5 minutes thence, we created them. These are referring to the statistics that we put in the population under the statistics area. We went earlier to the population. We opened the statistics, expando, and we did a plus, and we said, okay, we want a statistic that's a count statistic. It counts the people with heart disease. This is the criteria to apply to each agent. It says, hey, is this agent to be counted? Well, if this is true, it's to be counted. And this checks, are they in the heart disease state? Are they in this state? And same thing with, are they in this state? So it count the number of people who are in that state. Okay, now there's a few other things we need to frob with this time plot. First thing is, under the update window, it says how many samples should I keep around? I'm going to say keep around 1,000 samples, not just 100. It says how often should I update it? Every 1 year. Yeah, sure. And sometimes there's more things we want to frob here. For example, the time window that we want to show. We might want to change that too. Right now, we haven't really paid much attention to our time frame, but we're going to start to do so. I think I'll change this time window to be 200. We're going to run this for 200 years. We'll change the scenarios to accord with that. 200 model time units, which is years. If you want, you can select years here. Okay, let's go back to projects. So we're going to set the baseline scenario. Instead of stopping never, we're going to stop at a specified time. It's going to be 200 years. For this population, we're going to stop at a specified time. It's going to be 200 years. So both of these have changed. Now let's run them. Well, let's build first. Build it early, build often. Make sure it's a happy camper. If it's not a happy camper, let it know when they will offer their assistance. Okay, so make sure it's a happy camper, and now run it. Okay, we're not seeing it, but if we scroll up, here we go. Count with heart disease, count with no heart disease. Okay. This is a pattern that emerges from the model. Could anyone offer mechanistic understanding for these patterns we see in this data? Why do we see these patterns? Let's start with the obvious one. Count of people. Why is count of people with heart disease going up initially?
Well, initially, no one has heart disease, so they get not infected necessarily. They get the chronic disease.
Yep. They're developing chronic disease.
And then at the end, there's basically no introduction of more susceptible, so it ends up being basically no more people.
Hmm. Good. Yeah, there's a limit on how many people can get it, certainly. Although this doesn't nearly cover all people with heart disease. Now, why is this plateauing? Why is this not going up indefinitely? Sarah, you've mentioned one thing, like it can only be as large as the entire population. And maybe it would be nice if we showed the entire population here. Would you like to add something so we have a line for the whole population? Do you want to see that too? Would that be helpful? So we can reason about this? Why don't why don't we do
Well,
that?
we
Uh-huh.
assume the population is going to decrease over time.
It will. It will. Yeah.
But at the
Okay.
same time, if the rate of contracting heart disease is kind of low and they don't recover, I guess there's a plateau because of it.
I yeah, so it has a limit how far it can go up in terms of the number of susceptibles that can develop heart disease. If there's no one still susceptible to heart disease, it can't go up any further. But what's the other thing that that helps limit the rise, like how quickly it's rising? Let me ask this. What property, those who have some familiar with stock and flow modeling will know where I'm going with this. What property holds when it's flat, when it's not changing over time? What property is holding at that point? Well, the number of people getting heart disease on a per year basis is equal, if it's not going, if the total number of people with heart disease is not rising, the number of people getting heart disease must be equal to the number of people dying with heart disease, right? I mean, if the number of people with heart getting heart disease is bigger than the number dying who have heart disease, then the number of people with heart disease will be rising. By contrast, if the number of people dying from heart disease, or not from, with heart disease, is larger than the number of people getting it on a per year basis, the number of people with heart disease will be going down. It's like the water is flowing out of the sink faster than it's coming in. This is a sort of stock and flow modeling thinking that can be very helpful in interpreting aggregate behavior of agent-based modeling. Extraordinarily helpful. So I would say here, there's kind of a balance between people getting heart disease and people dying with heart disease. Oh, health disease. Yeah. No, it should be counting people with healthy heart. Thanks. Yeah. Um, we have we don't have a healthcare system. We have a disease care system, and if only they really invested heavily in health disease, then we'd be in better shape for prevention. Anyway, here it's going down. Why is it going down here? Why do we actually see a decline in people with heart disease? If they're never going to lose heart disease, why would we, if they're never going to, develop a healthy heart again, why would we be seeing a decline in the number with heart disease? Because what? People with heart disease are
People die,
people are dying with heart disease.
especially more frequently with heart disease,
Yeah,
probably.
they're dying with. So all of that is tied up in this. All of that is tied up in this curve. It's it's an entangled sort of interaction of these different terms. Why is the number of people with no heart disease, this yellow one, why is that dropping so quickly? So I want to address this first, and then I'll get to Russell. But why is this dropping so quickly? Give me two reasons. The number of people with no heart disease is dropping over time. What's two
I
ways,
think,
two mechanisms by
yeah,
which they could be dropping?
I think the people transitioning to heart disease and also dying from natural causes as well, right?
That's right. That's exactly right. That's exactly right. Some of them are dying from natural causes. So it's going down because of that. But there's another process involved as well that's also leading it to decrease, which is the developing heart disease. For both these reasons, it's going down. Russell, did you have something else to add? Your hands up.
Yeah, Professor, is there any age effect is considered here, or only that transition
Sorry?
that we draw in the state chart? Is the
Sorry,
age effect?
is there a what here?
Effect of age. Age.
Right now we have
Age.
no effects of age. Well, let's be
Okay.
clear.
Okay.
Is there, we have to be clear in our terminology. Is there an effect of age? Well, there's no explicit effect of age captured. The older someone is, the more likely they will have to have developed heart disease by now, right? So from a strictly associational standpoint, like if we were to not have, if we were put aside death and we're consider those who are living at a given age or of a certain age, they're going to be more likely as they age to have heart disease. Not because the model has some special propensity to develop heart disease, more and more risk of developing heart disease, not more and more risk per year of developing heart disease by an older age, but more cumulative risk of having developed heart disease. There's certainly that, right? I mean, like, they have more kicks at the can. Every year they have a chance of developing heart disease. So they're more likely by the time they're older to have developed heart disease by now. But there's no explicit effect of age right now. There's just this induced effect of, there's a cumulative risk of having developed it, just like we'd see in competing risks analysis or in survival analysis in biostatistics. The hazard rate right now of developing heart disease, given that you haven't already, right now, is constant on a per year basis. So, conditional on being in a healthy heart state, your chance of leaving on a per year basis is always going to be the same. But your chance of remaining in that state after a certain number of years is always going down. And in this case, it's going down both because you could develop heart disease and because you could die. So here we don't explicitly, we're not yet taking into account age. We will be going in that direction, and we could go in this direction after lunch with this model if you're so inclined, to have it explicitly consider age. But you have to recognize that, like, if you're thinking associationally, like, okay, we want more people who are older to have heart disease, that's going to happen anyway because of this, because they're more likely to have developed heart disease by that age, because they have more kicks of the can. It's not that they have a higher propensity per year right now in the model. We could add that though, and realistically, we'd want to add if we were trying to simulate a certain circumstance. Okay, maybe what I'll do is we're going to add one more statistic. We're going to go to population, and we're going to, actually, we don't even need to do it in population. We don't need to do a computed statistic. We'll just do it in this time plot. We're going to add to the time plot, click the time plot, add one more, and this will be population size. the entire size of the population. And the formula for it, the code for it, is going to be population dot size. Now, I want to comment a little bit. Jeff, maybe you could do a screenshot, a little shot of that up in the chat window. But I want to comment this notation. Here we're asking populations for its size. This begin paren and paren is referring to the fact that it's a function, or technically it's called a method, but it's some little routine that does a calculation. Thank you. It's like in high school we might have done the sine of a certain of 90 degrees or whatever. This is the information that the sine function needs to use its work. It's the so-called arguments of the sine function. It's its domain in a mathematical sense. It gives it the value that it's referring to the quantities in its domain. The values it needs to do its work to map to the output. Here it doesn't need any information. Size doesn't. Count healthy heart doesn't. But we have to do begin paren and paren to say, like, hey, call this thing. It just doesn't happen to need any information provided to it for it to do its work. It has all the information it needs in the population. Okay, so having done this, having added that to our chart, I am now going to run this model. And we'll now see a graph, and I'll run it as fast as possible. Here we go. Here's the total population. And there's the kind of people with heart disease and the kind of people with no heart disease and the population size. And as Larissa pointed out, we should have rightfully named this count with heart disease, not health disease. Heart, I did it again. Heart disease. There we go. Okay, now, some of you may say, well, wait a minute, a more natural measure, and indeed a dimensionless measure, I might add, that would be more, would add extra insight, would be what's the fraction of the population, or would certainly add insight, is what's the fraction of the people that have heart disease in this model. And so I'd like to create a little graph of that. Of the people still living, what fraction have heart disease? Okay, so to do that, we're going to go compute a statistic in population. Right now, both the statistics we have are count statistics. Oh, I should save this. Excuse me. So I'm going to save this, and I'm going to post it in case anyone would like a copy of it. They can go, well, I'm just going to do save as version 6, and version 6, and they're welcome to get it. So I'm just going to stop this recording.